Our last lecture for today, Zhao is going to start to tell us about Gauss sums leading up to the Weil conjectures.
I'm the last speaker, and hopefully you can still keep alert to listen to my talk. I'll talk three things today. First, I will talk about the Gauss sum, and then I will talk about the number of solutions of equations over finite fields. And then I try to relate these two topics, and then I will explain how we made this conjecture about the zeta functions for projected quadratic lines. So first, for the Gauss sum. The Gauss sum is defined for a character. So suppose I fix a prime p. I assume that is an odd one. And then I fix a character modulo p. See the non-zero elements here when we multiply is this kind to be a non-trivial homomorphism on this way to see cross. This is non-trivial. And also I fix an integer a. I assume that the integer a is prime. Under these notations, we find the Gauss sum of the character chi to be the sum x is from 1 to p. And it evaluates for each x, you evaluate the character chi x, then you multiply exponential so here this e to the z is the exponential function e to the 2. So this is the definition of the Gauss sum. Yeah.
Do you mean x goes from 1 to p times 1 or
1 from 1 to p. It's just all the congruence class of.
So,
oh, sorry.
are you assuming chi of 0 is 1?
Yeah. Thank you. This is not defined for at 0. I make this conversion, so it is defined for all the, if the integer is defined, it is divisible by, or if the integer is divisible by p, then I define it to be 1. This is a complex number, but it is a property that at the value of this complex number is square root p. So this is what I want to say for the Gauss. So keep this square root p in mind. This is the first thing, the first one.
Can you write a little bit lower?
Yes.
There's some quite small.
I'll write a line here. So I will write things below this line. Is that fine? Okay, and keep this first p. So this is the the first topic, the Gauss sum. The second is the number of solutions of equations for finite. So as a special example, I want to consider this equation. Consider y squared equals to x cubed minus x. This is an equation of two variables. And as you learned from the previous lecture, this defines an elliptic curve. And you know that to find a rational solution or find a rational point on an elliptic curve is a very difficult question. So I do not want to do this difficult question. I consider a relatively easier question. I consider the solution inside the fields Z mod PZ. Or in other words, I consider the solution if I mod out this equation by the prime P. And this is a finite set. So I can talk about the number or the cardinality number of this set. I denote it by NP. And the Gauss compute this number. We have a
How do you know that's finite?
because in this field you have at most it cannot be more than p squared, right? But actually this number can be
What do you think by the
it's a complex number.
so
Then you can talk about the argument. Gauss gives a very detailed, he compute this number, and now we know what this number is. Does anyone know the answer? What then? 1 plus p minus ap, but what is ap? There's no p in this equation.
Is the sum over things in AP of 1 plus the Lozano symbol of x.
Yes, that's what I'm going to talk about. But you know, you cannot compute the Legendre symbol, right? So actually, this number, this solution depends on the prime number p. So first, because here I assume p is an odd prime. So either p is congruent to 3 divided by 4, or p is congruent to 1 divided by 4. In the first case, the answer is very easy. It's just p. And actually, you can try to think of this by yourself. It is not very difficult. It's just a one-sentence argument. You can show that the number of solution is p when p is congruent to 3 divided by 4. I leave you as an exercise. This is a very doable question. But when p is congruent to 1 divided by 4, the answer is much more complicated. So to tell you the answer, I need to introduce some more notations. So now I assume that the prime p is congruent to 1 divided by 4. Then if p is of this form, p can be written as the sum of the squares of two integers. Okay? If p is congruent to 3 divided by 4, it is impossible to find such pair of integers. R and S are not unique, but if you require that R is odd and S is even, then R and S are unique up to some. If you further make the requirements that the sum of these two integers is congruent to 1 divided by 4, then R and S are unique. Okay? Then under these notations, the number of solutions over this finite loop is given by p minus 2. This is a very difficult result, and I think if you can solve this question by yourself, then that means you have a very good talents in mathematics. So try to challenge yourself to think about this, the second result. But if you cannot find the result by yourself, you can find how to compute this number in many number theory books. For example, this one, a classical introduction to modern number theory. Then you see how Gauss computes this number. But we do not go through the details of the proof of this result. What we really care is the difference of this number of solutions with the prime p. In the first case, the difference is just 0. In the second case, difference is 2r. But here, r squared plus n squared is equal to p. So the absolute value of this r is smaller or equal to the square root of p. So in other words, this difference is bounded by 2 times square root p. Okay, so we have another square root p when we compute the number of solutions of the equation over finite loop. So the question is, here we have a square root p when we compute the value of the Gauss sum. Here we have a square root p when we estimate the number of solutions for this equation over the prime field at z mod pz. Then it is just a coincidence we have square root p in both of these two settings, or there's a relation between them. And the following, I try to explain by an example, so that actually there is a deep relation between these two factors. But before I move on, I want to make one more remark on this number. So, if you want to compute this solution, how can you compute this? You can first fix the value of z, and then try to find the number of y's such that the square of y equals to this fixed number. Then, if you want to simplify this this sum, I need to introduce the so-called Legendre symbol. The Legendre symbol is a map from z mod pz to, it takes values in, its value can only be 0, 1, or -1. And it is 0 if a is 0. And it is 1 if a is a square in z mod pz. But it is not 0. And it is -1 other places. Then, if you forget, you just restrict this map into the non-zero elements in Z mod PC, you'll see that this gives you a quadratic character of the group in mod PC. Okay? Then, under this notation,
Could you
we can write
bigger?
this number of solutions.
Ben, could you write bigger, please?
Oh, yeah. We can write this number of solutions in terms of the Legendre symbol. It's 1 plus this Legendre symbol. Because if this is a perfect square, non-zero, then you have 2 solutions. If it is 0, you have only 1 solution. If it is not a perfect square, you have no solution. Okay? And then, try to simplify this sum. You have p ones. You sum them together, you get p. And the rest thing is the sum, is Legendre symbol. And this inequality just gives you a bound on the sum of these values of the Legendre symbol. It tells you that the eigenvalue of this sum is less or equal to 2 times square root p. Okay? So in this remark, we try to write the number of solutions of an equation in terms of the sum of some characters. And in the following example, this trick will be used several times. So in the following, we try to compute. We consider a homogeneous equation a0 x0 en plus a1 x1 en plus ar x to the r en equal to 0. This is a homogeneous polynomial. And here is a0, a1, r. We have non-zero elements over a finite field. So here this fq is the finite field. With q elements. And q is the power of the prime p. If you do not know much about the finite field, you can just think about fq to be the prime field Z mod pt. You will not lose anything until the end of today's lecture when I define the zeta function of a projective one. So here I have such a homogeneous polynomial. I make one more assumption. Assumption is n will divide the number q minus 1. This assumption is not necessary for the discussion. It just makes the discussion much more simplified. And then I denote this in q to be the number of solutions of this equation star, or star, in the finite field at Q. I want to compute this number. But actually, for such a homogeneous equation, we do not know much. We do not know many methods to compute it. So we can try to reduce this complicated equation into some simple equation. What is a simple equation? A linear equation should be an equation which is simple enough. Okay? On the other hand, you can see that another type of equations. You consider the equation of this group. A power of the variable x is equal to some given number. And similarly, x1 n is equal to u1, and x2 xr n is equal to u. So first we have a linear equation, and and the rest r plus 1 equations. They are not linear, but they are simple. If you try to solve this equation, it is equivalent to solve this homogeneous equation, because you can just take x0 to the n to be u0, take x1 to the n to be u1, and take xr to the n to be ur. And if u0, u1, ur satisfy this linear equation, this x0, x1, xr will give you a solution to this homogeneous equation. Okay? So this is equivalent to this homogeneous equation. Then this interpretation gives you a way to compute the number of solutions of this homogeneous equation in the finite field at Q. Because if you write the equation in this way, you can first fix the value of u0, u1, and ur. So here this lu is a function, it's a linear function of the r plus 1 tuple. You have such a linear function, then you just first you fix the value of this u0, u1, ur such that this linear function is 0 with the given values. Then you try to compute the number of solutions to each of these single equations. And then you can write the number of solutions of this equation as the sum of these products. Here, is an I, ui. For each of these factors, it's just the number of solutions for each of these equations. Which is the number of solutions of the equation x to the n equals to I to the n equals to. In other words, you compute the number of solutions for each of these functions, and then you multiply them together. You get the number of these system of equations for the fixed value u0, u1, u_r. And then you take the sum for all these u's, which satisfy this linear equation to be 0. Then you can compute the number of solutions of the original homogeneous equation. But it seems that under this expression, it makes this number much more complicated. But we can do some analysis, try to simplify this sum. First, we can give a very simple description for this number. If we want to compute the number of solutions to this equation, actually the answer is not very difficult. It is 1 if this ui is 0, because xi to the n, if xi to the n is 0, of course the only solution is xi is 0. And if you have n solutions, if this ui is an nth power in the finite field Fq. Or in other words, if this ui can be written as an nth power of some elements in Fq, then you can show that actually this equation will have exactly n solutions. This is because the multiplicative rule of the field Fq, this is sigma. And if this ui is not an nth power in the finite field Fq, then of course we have no solution to this equation. So it might look a little bit complicated, but understand difficult things, it is better to check this for some simple examples. For example, I will leave you as an exercise. You can try to check this fact for if this is a quadratic equation. You can go back to the Lagrange symbol I explained in the previous example. So now we have a very clear description for each of these factors, but it is not good enough. You know, in the previous example, we tried to write the number of a solution of an equation as the sum of some characters. And we want to do the same thing for these numbers. I try to write this number as the sum of some characters. So to do this, first you need to have a good understanding of characters of the field Q. So here we use the fact that the multiplicative group of this field is cyclic. In other words, we can find a generator, which is called, denoted by W. As the multiplicative group of the finite field at Q. Then any character chi of this multiplicative group is uniquely determined by the value of the character as this generator. So we know that it should be of the form denoted by chi alpha. This chi alpha is a character, it's a homomorphism from this multiplicative group to C cross, and such character is uniquely determined by its value on a fixed generator. And because this omega is a finite order element of order q minus 1, so the image or the value of the character at this generator should be an order at most q minus 1. So it should be of this term. Alpha, here this alpha is a rational number, and q minus 1 times this alpha must be an integer. Okay? So in this way, we list all the possible characters of the multiplicative group of this finite. But here, actually, we do not need to consider all the characters. We only consider those characters whose order can be divided. Whose order is can be divided by is divisible by n. So as I said, I try to write this number as the sum of characters of the finite field at Q. And here is the fact. It's Ni.
Divides it?
Yeah, divide them. Thank you. It is a sum